Hi, we're Team 3, and we're going to briefly present our progress on our project entitled A Predictive Model of Urban Waste Generation by Zip Code. Our project is looking at municipal waste in Austin, Texas, a city in the United States. Why model waste generation? Well, waste generation rates are not homogeneous in the city, so planners really benefit from being able to predict waste generated to right-size waste management services. We have four objectives in our project. One, identify the attributes that influence waste generation. Two, understand the relationships by testing correlation. Three, generating a model to predict waste. And four, testing the model on reserved data.
The methodology of our first objective is to extract and merge data from 187 garbage routes and 44 zip codes. After that, the set of attributes from years of census and garbage routes data is reduced by filtering missing and inconsistent variables. This improves the consistency of the datasets and allows the two subsets to be better joined based on their zip codes. For our second objective, we further look into understanding the relationships between the reduced set of attributes using correlation analysis and visualization tools to select best classifiers to our problem in predicting waste generated considering ever-changing socioeconomic variables in different zones of the Austin municipal area.
After preparing the ultimate dataset and performing the data preparation steps, we can go for modeling according to CRISP-DM procedure. We're going to apply both unsupervised and supervised learning methods. K-means clustering will be used to find the clusters of high, medium, and low waste generation in zip code scale. Predictive models are also being developed by two supervised learning methods of decision tree and naive Bayes. The objectives of these techniques are to classify the waste generation level and pattern in different zip codes of Austin, Texas, given the relevant socioeconomic parameters. After developing the models, metrics such as confusion matrix, AUC-ROC curve, and lift chart are going to be used for model evaluation and comparison. The final step is model validation over unlabeled data. In order to do this, split and cross-validation approaches are going to be followed. In split validation, 10% of the data is put aside as the test set and used for model validation. Tenfold cross-validation will also be carried out to find the average accuracy of the predictive model over the whole dataset. Accuracy measures such as root mean square error, sum of squares, Davis-Bouldin index, and mean absolute error can be used in each step and depending on the model type to test its goodness.
Our dataset is from two sources, the US Census and the City of Austin's Open Data Platform. From the US Census, we took socioeconomic data on housing, population, and income by zip code. And from the City of Austin, we took waste generation data per garbage route, which includes the route numbers, the dates, and the load weight, which is our target for prediction. In order to merge the two datasets together, they need to be on the same scale. This could only be done on GIS. We first found the centroid of each garbage route. This method calculates the centroid based on the shape of the polygon. And since most of them are irregular, this method prioritizes placing the centroid towards the larger sections of the polygon. And then we intersected the garbage routes with the zip codes. This combines their datasets. Now each centroid is assigned to one unique zip code, even if the garbage route is not fully contained within the zip code. Now we can merge the waste and census data based on their common zip codes for a final dataset of 11 attributes and 201 examples.
Now it comes to the initial EDA section. The total waste value for each zip code varies from year to year but remains within a reasonable range. The zip code scale minimum total waste is 686,680 pounds a year, while the max value is over 20 million pounds. When we use the x-axis as the population and the y-axis as the total waste for year to make a scatter plot, we can see that these two variables have a relatively obvious linear relationship. The total waste is clearly the most correlated with population figures, as well as with occupied housing units. There's a very minor correlation with the average household size. We also see that attributes like employed population are highly correlated with the occupied housing units. The data needs some normalization to tease out how much a population attribute like the employed population correlates with the waste when normalized to the total population.
What's next is to continue with the data preparation, train different models, check their accuracy, and apply a final model.